Hi, Year 11. I just want to talk to you about the GCSE specification for Paper 1 Chemistry. And what I'm going to do is I'm going to just jump straight to the specification. Notice that specification tells you quite a few important things, and it's always worthwhile going back onto this to have an idea to finalize a revision. So we're going to start with atomic structure, discuss something in bonding, maybe look at something quantitative, look at chemical changes, and then finally any changes. Let's start with atomic structure. So here it talks about pretty straightforward things. Please feel free to either pause and take a closer look. We know that all substances are made of atoms. Atoms of each element are represented by chemical symbol. So you need to know your chemical symbols at least up to calcium. If we go a bit more forward, it's talking about compounds are formed from elements by chemical reactions. Okay, so here chemical reactions can be represented as word equations or chemical symbol equations using formulae. So for example, if they said iron, okay, reacts with chlorine, okay, to form iron chloride, and they've given you the equations, okay, sorry, they've given you the symbols for each. So suppose they gave you FeCl2 and FeCl3, okay, we just have to be in a position to write the balance equation. So here it is, Cl2 reacting with chlorine to make FeCl3. Notice that when we balance, we have to put numbers in front, okay? And all this is asking is to put a coefficient in front of the three substances to make sure that all the atoms on the left-hand side are equal to atoms on the right-hand side. You can see that the telling sign is the 2 and the 3 for the chlorine. So I'm going to try and think of a common number. I'll put a 2 there. That tells me now I've got 6 chlorine. So I'm going to put a 3. Okay, that's now balanced the chlorines on left and right. I've got 2 ions here. So obviously I have to put 2 ions. Okay. You must use the periodic table, okay, and pay close attention to groups 1 and 7, okay, and I will go to those in a moment, okay. Let me clear the board. So if we look, it's talking about mixtures. You know, mixtures consist of 2 or more elements or compounds not chemically combined, and that we can use those chemical properties of those substances to separate them, okay, yeah, because mixtures aren't chemically combined. So mixtures can be separated by physical processes, just filtration, crystallization, right? Crystallization appears in chemical changes, so you need to know how to make a salt. Simple distillation is very straightforward. It's a process of separating mixtures of liquids where the lowest boiling point will gain enough energy and change state. Okay, so that's your first stage, state change from liquid to gas. And then if you remember, those gases, if you have a mixture, those gases, okay, will then travel through a condenser, okay, and there'll be another state change, okay, and that will be obviously gas to liquid, okay, gas to liquid, which is condensation. All right. Okay, and it's saying here, describe and explain and give examples of specified processes of separation. That actually appears paper 2, where you have to be aware of fractional distillation. It says here, suggest a suitable separation purification techniques for mixtures when given appropriate information. So be aware, if it mentions distillation, the most obvious thing is to think, have they given you liquids, a mixture of liquids? And if they have, use those properties, okay? Use those properties. So if one of the liquids is going to have a lower boiling point, you know that it can be evaporated easily, state change from gas to liquid with lower energy, and then what will happen is it will condense, turning into a liquid in the condenser. Okay, you can use others such as filtration. So suppose that you have a mixture of 2 liquids where one is soluble in another chemical, but the other mixture is insoluble, then of course you can filter it. All right, let's move forward. It's saying here, all right, that we've got some experimental evidence, new experimental evidence led to scientific model being changed for the development of the model of the atom. So just remember, we've got the discovery of the electron, which led to the plum pudding model. So what did J.J. Thomson suggests? He suggested that the atoms are a ball of positive charge with negative charge electrons embedded in it. Now, this is the important thing. It's the alpha scattering experiment. Okay, so you need to know key observations here. Okay, so first and foremost, remember that you have, okay, the first thing, which is J.J. Thomson's plum pudding model, okay? And you've got this stretched out region of positive charge. Notice that this positive charge changes from Rutherford's because Rutherford says, okay, that it is concentrated at the center. So this dense region of positive charge. Also realize that when you bombard alpha particles, which are themselves positive charge, if J.J. Thomson was correct with his plum pudding model, these should just go straight through. But this is the difference. There are three important observations. The majority of these alpha particles went straight through. Straight through suggests empty space. Okay. The next thing, you see deflection. Now, deflection is telling you when two of the same charge particles, they get close to each other. And so what happens is you have a sort of repelling effect. This is going to deflect, i.e. change direction. This was observed. This then instantly gives the idea that the nucleus must be a dense region of positive charge. Second, and finally, most important, which I shall label here in orange, an alpha particle, right, infrequently, right, and very rarely would collide with the nucleus and bounce straight back, okay? So please try and remember that Rutherford's nuclear model is suggesting that the positive charge is a dense, concentrated region right in the nucleus or in the center of the atom, okay? And the atom has a nucleus which is surrounded by empty space, and that you find your electrons orbiting around it, which I should draw here in blue, okay? They are in orbit. Now, how does this model change to Bohr's model? Bohr then suggests, obviously, that the electrons occupy fixed regions, okay, called shells, okay? Right? And you know that the highest energy level have electrons furthest away from your nucleus, all right? And you'll realize that it's these electrons that are involved in bonding. All right, so if we just keep on going, that's Niels Bohr. It says here, later experiments showed the idea that the positive charge of any nucleus could be subdivided into a whole number of smaller particles, each particle having the same amount of positive charge. So there you go. The positive charge of the nucleus is incredibly important, and that is due to the protons, and that is your unique identifier for an element. So if you have 7 protons, you know that's nitrogen, whereas if you have 6 protons, you know that is carbon. So James Chadwick then provided evidence to show the existence of neutrons. If you see a statement with James Chadwick, your mind has to suddenly start thinking of the word isotope. Remember what isotope means? It means that they have the same number of protons for an element, but different number of neutrons. Okay, if I move forward, yeah, this is all pretty basic stuff here. All right, it's saying here details of the experimental work by Niels Bohr is not required, and of course detail of Chadwick's experimental work is not required, but you do need to understand and be in a position to explain why new evidence from the scattering experiment gave an idea of the changes, okay, to our atomic model. Remember what I discussed earlier. Please play that back, okay? The difference between the plum pudding and the model of the nuclear model is pretty easy. I don't really expect that to be in your chemistry paper, okay? We've got this, the number of protons in an atom of an element is the atomic number. That's pretty easy, okay? And for an element, you have the same number of protons as electrons. So that explains why atoms are neutral charge. Okay, if we move forward, yeah, being aware of these numbers, look at that, the atoms are very small. The radius is 0.1 nanometer, that is 1 times 10 to the minus 10. Okay, the radius of a nucleus is less than 1/10,000th of that of an atom. So simply, can you see that they've gone from 1 times 10 to the minus 10 to 1 times 10 to the minus 14? That is, of course, 10,000 times smaller. Okay, let's move over to this. You should be aware of the relative masses for the proton and neutron, and explain as well, if you're given data like this, how you can use this to help you work out the number of neutrons. Okay, simply do 23 less 11. So then it comes to relative atomic mass. This could be asked as a definition. This is the definition, is the average value that is accounting for the abundance. That means how common, okay, the isotopes are present for an element. So suppose you you looked at a bar chart, okay, for boron, okay, you'd notice that boron has two isotopes, one at boron 10, okay, and the other at boron 11, okay, and they have an abundance of, I think, approximately 20% for the boron 10 and about 80% for boron 11. So you know, that is 80%. So you obviously know that if it's a average weighted mass, then it instantly tells you there must be a greater, you know, abundance of the boron 11, because when you calculate the relative atomic mass, which is simply 10 times 20, okay, added to the 11 times 80, you'll end up with a value when it's divided by 100 of around 10.8. Now that 10.8 closer to 11 tells you that obviously the boron 11 isotope is much more abundant. Okay, let's move forward. Okay, so electronic structure is pretty easy. Okay, yeah, it always follows that order of 2 in the first shell maximum, followed by 8, and then followed by 8. The last shell that you need to be aware of is with calcium. All right, calcium has got 20, and that means that the electron configuration of calcium will be 2, 8, 8, and 2. Now, the last number tells you what group it's in because it has 2 electrons in the outer shell. Let's move forward. The periodic table. Now, the periodic table is obviously arranged in order of atomic number. And so the elements with similar properties are in columns known as groups, okay? So they have similar properties. Now, this idea is going to be really important. When we say similar properties, that means both chemical and physical. So that means how they react with, say, oxygen, chlorine, or how they dissolve, to things like physical properties, such as what temperature they sort of melt or boil, okay? And there is a very important thing here when it comes to the development of this. Okay, so let's move on to that. The development of the periodic table. So this is now really critical. I want to just, you know, focus on some of this stuff. Okay, we've got here a very clever person, Mendeleev. Okay, now what's important about Mendeleev is that he overcame problems, because what earlier scientists did is that they classified the elements, okay, by arranging them in order of weights. He did the same thing, okay, but what he did, he left gaps, okay, and he didn't necessarily follow the weight rule. So if you put a load of elements according to weight, you'll inevitably end up having some elements in wrong groups, okay? So what did he do? He left gaps, and he waited, okay, for some of those elements to be discovered. And in fact, some of those elements were discovered well after his death. So what he did, which was quite clever, he looked at those gaps and he looked at the elements around it. That means in the same group, maybe above or below, and to the left and right. And by their location and position, he was able to accurately predict a lot of chemical properties, okay? And this is really important, right? Because that's how we appreciate the modern periodic table as being derived from what Dmitry Mendeleev put together, okay? So it's saying here, knowledge of isotopes made it possible to explain the order based on atomic weights. I'm not always correct. Yeah, you can have some isotopes which are heavy, and if we were going by atomic weight, they would end up being in the wrong group. So this is also backing up Dmitry Mendeleev's idea of leaving gaps. Okay, let's move forward. We've got now here, so this is obvious. Yeah, elements that react to form positive ions are metals, yeah, and they form positive ions because they lose electrons. Elements that do not form positive ions are non-metals, and they tend to form negatively charged ions, okay? This is pretty straightforward stuff. Let's see if we can see anything important. Yeah, explain how reactions of elements are related to the arrangement of electrons in their atoms, and hence their atomic number. So, okay, let's take a look at this. We've got lithium. All right, lithium is Li7. That means it's not 7, sorry, it is 3. So that means it's 2, 1 in terms of electron configuration. And sodium is sodium 11, that means 11 protons, hence 11 electrons. So that's going to be 2, 8, and 1. We know that when both of these react, they're both going to form positive charged ions. Okay, and in a moment we'll have a look at the ease at which sodium forms positive ions compared to lithium. Okay, because you have to be aware of some chemical reactions and properties of group 1. Group 0 is pretty easy. Yeah, just have to be aware that the boiling point of the noble gases increase with relative atomic mass. Let's move this down towards group 1. So it's saying here the elements of group 1 of the periodic table are known as the alkali metals. So why is that? Let's link that to chemical changes topic. If I took a metal in group 1 and reacted it with water, okay, it would dissolve, it would fizz, they're low density, they sit on the surface. What they'll form is metal hydroxide. This is known as a metal hydroxide, okay? And this metal hydroxide is soluble and hence is an alkali. You also produce the gas hydrogen, okay? Now watch carefully, I'm going to just put some numbers here to balance it. Okay, we can see that there's a bit of a problem here. We've got 1 hydrogen, 2 hydrogen, so there's 3 on this side, whereas we've got 2. Let's try and make everything even. I'm going to put 2's in front. So now I'm saying to you that all of the metals in group 1, okay, react like this, okay, forming metal hydroxides, which are alkali. So hence we call them alkali metals. This solution has got a pH above 7 because when it dissolves, it liberates the hydroxide ion. And you know this, if the hydroxide ion concentration is high enough, then what will happen? The pH of the solution will be above 7. Now, the ease at which, for example, sodium releases its electron is to do with its atomic structure. Okay, we know lithium has got a shell and then its last energy level, okay, it can lose that electron. But just notice that this has only got 1 shell, okay, before the last shell. And so we can say that nuclear attraction is going to be quite strong. If we compare this to sodium, though, we notice that sodium does have, okay, 2 shells before the last electron. And what this is doing is this is keeping, this is trying to keep the electron in place, but because this electron is further away, it is lost easily. So sodium has a much more greater tendency to lose an electron compared to lithium, and hence sodium is more reactive. And if we go down the group and look at potassium, then potassium is even more reactive, okay? Because for the same reason that it loses the electron more readily, because the inner shells are blocking, okay, the attractive force of the nucleus, and we call that a shielding effect or screening effect. Now with group 7, this has happened before. How do we prove group 7 elements are less reactive at the top? More reactive at the top and less reactive as you go down. Well, let's take a look at fluorine, for example, and compare that against bromine. Okay, fluorine is closer to the top, okay, whereas bromine is closer to the bottom of the group. Okay, and we can see here that fluorine does only have 2 shells. Its electron configuration is 2,7. Okay, it needs to gain an electron. Now, bromine, which is further down the periodic table, has a few more shells, okay? I think it's in period 4. So if it was to gain an electron, the attractive force is not going to be as great between the nucleus and the electron compared to fluorine when it gains the electron in its highest energy level. So for that reason, fluorine atoms, notice how I say that, fluorine atoms gain electrons more readily. And that's why fluorine is more reactive. And of course, you do know this connection with redox reactions. Because fluorine is gaining an electron more readily, okay, it turns into the fluoride ion. Okay, now there is a way of proving the reactivity of these halogens, and that is simply by reacting the salt of these halogens with the halogens themselves, okay? So we call the salts halides, so that would be like fluoride, and the salt would be called sodium fluoride. So for example, if I took sodium, let's take sodium bromide, okay? Sodium bromide, okay, there it is, okay? And if we reacted that with chlorine, okay, so notice that it's on its own, it's a halogen, we're going to form sodium chloride, and of course, we're going to form bromine. Okay, now I'm just going to balance this out. I'm going to put a 2 here and a 2 here. That balances the matter. And notice now that I'm going to put this into an ionic equation, and that will simply be written by removing the sodium, which is what we call a spectator, right? It doesn't chemically change. We've got 2Br minus reacting with chlorine, forming, okay, 2 chloride ions and bromine. Now, chlorine is above, okay, bromine in the periodic table. Chlorine is more reactive than bromine because it is above. So chlorine will be able to, here it is, gain the electron more readily. So it forces the bromine to displace. Okay? All right. And this is what we mean here. The more reactive halogen can displace a less reactive halogen from an aqueous solution. So when this happens, you should notice a color change, okay? The bromide, the sodium bromide, okay, should be a straw-like color. And when this chemical change occurs by adding drops of the chlorine halogen, it will go a sort of deeper browny sort of orange sort of color, okay, to prove, remember, a color change proves a chemical change has occurred. Okay, let's move this forward. All right, so transition metals are pretty interesting. So for example, if I took iron, yeah, iron can form chloride, such as FeCl2, or whoops, FeCl3. That's interesting. We've got an element that can actually form 2 different types of chlorides, yeah? So that must suggest that this is Fe2 plus, and that must suggest that this is Fe3 plus, okay? 2 plus and 3 plus, right? But if we looked at sodium chloride, it only ever forms 1 type of chloride, suggesting that the sodium is Na plus. So this iron, this element iron, is a transition element, transition metal, because it can transit and move between different charged ions, okay? All right, and that is really important. So these transition metals, you can imagine when they were putting the periodic table together, the earlier versions would have probably shown a few of those transition metals being thrown into potentially group 1, group 2, even group 3, okay? Obviously with more chemical reactions and more discoveries of the neutron, they're able to actually put them in their correct place. Okay, let's move this forward. Okay, it now goes into bonding and structure. You should know the difference between covalent, metallic, and ionic. I have to remind you, covalent is between non-metal and non-metal. Metallic bond, okay, is honestly, it's just the attraction between your metal ions and delocalized electrons. We describe that delocalized electrons as a sea of delocalized electrons. So that's your metal ions. Yeah, I'm going to draw them in a nice regular arrangement. They shouldn't be touching. So let me just move that slightly to the left. There we go. And here's another layer. Okay. And what we have is a sea of delocalized electrons. There they are. Okay. That's your sea of delocalized electrons. So the metallic bond is described as the strong electrostatic force of attraction between the positive metal ions and the sea of delocalized electrons. They form layers, and this should help you understand that these layers can slide over each other, which gives the property of metals being malleable. Yeah, so we can already look at the structure and the bonding and suddenly start to realize some properties such as this one. Yeah, metals are malleable. That means they can be struck and they can change shape. Now, covalent bonds, okay, you use the word molecule, okay? You use the word intermolecular forces, okay? You only describe those for covalently bonded entities, okay? Please be careful not to describe metallic properties using the term intermolecular force. You will not get marks, okay? And that's a really big sacrifice. I also needed to know the definition of the covalent bond, which is simply a shared pair of electrons, okay, between 2 non-metal atoms, okay? And that's really important as well. What these atoms do is they try and obtain a full outer shell. Ionic bonding is pretty straightforward. That is between metal and non-metal. Please realize ionic bonds, okay, are occurring because the positive metal ion is attracting a negative metal ion. And how they became positive and negative is because one had to lose an electron, hence becomes a positive ion, and the other had to gain an electron and hence become a negative ion. The ionic bonded structure is known as a lattice. Have you noticed that I've not used the term intermolecular force? If you do, you will lose the mark. So why do these ionic bonded substances conduct electricity? Well, obviously, if they're in a fixed lattice, they will not move. These ions are held in a fixed lattice. But if we were to melt this lattice, now it's molten, those ions are free to move and transfer and carry charge. Okay, so let's move forward. That's a lovely diagram. You could be asked to describe the process which leads to the production of sodium chloride. Notice the change in electron configuration and notice the charges. And remember, the ionic bond is described as the strong electrostatic forces between oppositely charged ions. Okay, so have a quick flick of this. You should be able to draw at least a group 2 halide or a group 2 oxide, yeah, and that should cover it. Yeah, they're only asking for group 6 and 7, that's the oxide or halide, and group 1 and 2, so that could be like lithium or magnesium, group 1, group 2. That is your lattice structure. Notice those lines represent the ionic bonds, and you should be able to deduce the formula of this just by simply counting the number of solid grays and then counting the number of light grays and then getting that down to its simplest ratio. That will give you the formula of the ionic compound. Okay, I'm going to move forward. Yep, this is a dot and cross. Yeah, showing this is lovely. This is a lovely arrangement. This is telling you about the electrons in the outer shell and how electrons are being shared. This is the same thing, just without circles. Notice that we've got the stick diagram, the stick. If you ever see a diagram with sticks, brain thinks covalent bonds. If you see a ball and stick, you have to be quite savvy. If they've told you that this is a carbon and this is, for example, or let's suppose not carbon, let's suppose that's boron, okay? All right, and let's suppose this is chlorine, and you see a kind of like a thick line connecting the two. Well, obviously, I can see 1 boron, 3 chlorine, so that's going to be BCl3. Okay, they do have their limitations. You'll notice that this doesn't tell me about the 3D arrangement of bonded atoms. This does tell me the 3D arrangement of bonded atoms, but it doesn't tell me how electrons are being shared. Okay, let's move forward. This is a representation of a polymer. They're assessed more in paper 2 chemistry. Now, if we move a bit more forward, you'll notice here that we're talking about about the metallic bond. Okay, and we've got states of matter. And that should be it, okay? This was assessed, polymers were assessed, okay, in the last year's paper 1. Please review that. Remember, polymers are large molecules, they have stronger intermolecular force, and therefore they require more energy to break, only because the molecules are bigger. Giant covalent structures, you should know your allotropes of carbon, that's graphite and diamond, and that leads on to things like graphene, which is a single layer of graphite. And just recall that alloys have different radiuses, different atoms mixed in, okay, with different radiuses. And so what does that do? That distorts the layer. And by distorting the layer, that makes alloys very strong because the layers cannot slide. That is it from me. I'm hoping that you're going to read the specification further, and I wish you the very best of luck in your exams. All the best.